All right, good morning. Okay, let's continue on a partial derivative, and we'll finish this multivariable function, okay, which will be basically the last lecture that will be included in the midterm exam. Let's do a quick review at here. This is what we have covered in the previous lecture. Basically, we introduced what multivariable functions are. What does it look like, right? Now, as I mentioned in the previous lecture, you can visualize. So you can visualize function of two variables. Okay, in 3D space, this is okay, but you cannot visualize a function of more than two variables. Okay. Now, there are different ways to visualize a function. You can simply just graph it out. And in this case here, it's a surface. And you can also use so-called contour plots to visualize a function of two variables. So contour plot, basically you're slicing this surface with a different z value, with the different planes. And that intersection between the slice plane and the original surface is this contour. So contour essentially means everywhere along that contour curve, the z value is the same, so all the same altitude. Or you could, for a function of three variables, you could do a so-called level surface. Basically, let w equal to a constant, then you would obtain a constant surface. So that's pretty much as far as you could do in terms of visualizing a function of more than two variables, or function of three variables. So I wanted you to be able to graph very simple surfaces like a plane, paraboloid, right? These kind of simple surfaces. And then we talk about the started calculus of a multivariable function. So calculus basically means how about derivative, taking integrals of multivariate function. So today we'll finish the derivative, and then later we'll get on to the integrals. Now, instead of just directly calling a derivative of a multivariate function, because we have more than one variable, so now we have the so-called partial derivative. Okay, so partial derivative of this multivariable function. And the definition is defined like this. If you have a function three variables, then its partial derivative with respect to x is defined as this limit. And if you look at this limit at here, the only difference is instead of a straight d, derivative used to be a straight d. And now we have the so-called partial d or curved d. And of course, you still have those multivariable yz at here. But other than that, the formality of taking this limit is very much similar to the function of single variables. And similarly, you can, if it's function two variable, and then you can define this partial derivative as it is. Okay, so this is more a general case, than this one here. Okay. So that's partial derivative. Now let's take a look at the actual computation of a partial derivative. Okay, well, three examples. But before we move on at here, okay, let's look at the way it's defined, the partial derivative. So the way it's defined is essentially you increase your x by a small quantity delta x. So that's what it means, right? X plus delta x. And the y and the z, you look at the y and the z here. Basically, they are being kept as what? Unchanged. So if you look at this definition, the only thing that's changing is the x. You're only increasing the zx with a delta x quantity. And the y and the z at here are being kept as unchanged. In other words, we can consider this y and z at here are constants. Okay, so for this partial derivative, this is crucial right here. Okay, so this is something. Let's put a note here. So consider y and z as constant, because in this definition, the limit set here, even though they are variables, but the only quantity you're changing in order to obtain this partial derivative is x. So there's only delta x change. So when it comes to the computation for the partial derivative f over the x, we will consider the y and the z as constants. Okay, so I'll show you what it means, and also I will the typical pitfall set here. You know how your mind will keep trying to trick you that they are not constants. So let's take one example. Okay, so here is a function of there are only two variables, so I don't really need a z over here. Here's a function of two variables. It's y times sine xy. Okay. Now, it does actually involve a property at here, more or less like a chain rule. Maybe I'll write it down first. Okay. So a general format like this is this. So if you have a z equal to f of x, y, okay, and in this case here, okay, actually, sorry, it's not quite. That's okay. So, and this formality here is like this. Okay. So this function f consists of two portions, two parts. One is u, one is v. So essentially, it's like this: u here is the y, and v here is the sine xy. Here is the v at here. So there are two terms at here, right? Two terms. Now, so basically, if you think about function single variables, when you have a function f equal to single variable u times v, and there is this simple product rule, right? You can use to calculate this derivative. So we will try to apply this product rule at here as this for this example. So if you're trying to calculate partial f over partial x. Okay, let's try to calculate partial y here. Let's try to calculate partial f over partial y. So the product rule to apply for this kind of situation is, so partial f over partial u first. Sorry, actually, my bad. So partial u over partial y first, and then times v, and then plus the u, and then partial v over the partial y. Okay, that's a product rule. Okay, so it's like a u prime v plus v prime u, okay, for function of single variables. Good? Yeah. So let's take a look at the. Now substitute the actual function into this into the formula now. Okay. So u is y at here. So even u is function xy, but u is really just a y at here, right? So it's not really a partial now. It's just actually just a direct straight du over dy in this case, because u is just a function of y. Okay. So, but anyway, so we can still write it down here. So partial y over partial y times v, and v is sine xy. Okay, and then v, and the second term here, u is y at here. Partial v over partial y. So partial v is sine xy. So I'm going to write down here sine xy. So that's how you substitute everything. Okay. So now do the actual computation of the derivative. So the first one here, so partial y over partial y with respect to straight dy over straight dy, which is what? 1, right? Yeah. And then sine xy, okay, plus y times, now this term here, partial sine xy over partial y. So this is where you need to consider the x variable as a constant. And this is something, this simple here, it shouldn't be too bad, okay? But always remember, your mind will play the trick. Even though you're telling yourself, I'm going to consider x as constant, but your mind will keep telling you it's not a constant, it's a variable, which is actually alright, because it is a variable, but you're just temporarily treating it as a constant. So if I'm treating as a constant here, you could just think of it as, let's say this is 2y, or temporary, or 3y, right? In order to make your mind actually believe it is true. So you end up with, if it's just like you're taking, let's say, what's the derivative of sine 2y over y, right? dy. So everybody knows this is 2 times cosine 2y. So in this case here, I consider x as constant, so I get x times cosine xy here. Okay, so that's the gist of partial derivative. Okay. It's actually computation-wise, if you look at the derivatives, nothing different from function single variables, except you have to think of x here as a constant. Okay, so a little bit of simplification, just tidy up things. Really, there's nothing to simplify here. Okay. So that's the results for this one and here. Okay. So when you take derivatives, you can through this very simple example. I'll give you another one just shortly. Okay. As you can see, the operation or the computation at here, okay, is the fundamental is that function of the single variable calculus. Okay. And all you have to be careful is which one should I treat as a constant, right? And if you're not too sure, just look at the variables you're taking partial derivative with respect to, okay, and then the other variables are being kept as constants. Okay. So before I give you another example right here, so let me maybe go over a simple concept now. Just a simple question maybe. So what does basically partial f over partial x, for example, okay, at a certain point, okay, what does this mean, right? What's the physical meaning of this partial derivative at a certain point? Okay. So basically what we're looking for is the geometric meaning, okay, of this partial derivative at a certain point. Okay. And I think I'll start with df over dx for function of single variables. Okay. So this function single variables, and we all understand that if I take derivative f over dx, so this is derivative, this one basically means it's a rate of a change. Okay, it's a rate of a change of this function f with respect to x. Okay, that's the basic meaning of function of single variables, right? Rate of change is essentially it's a velocity concept. If you change this small x, how fast this function f will increase or decrease. Okay, that's what df over dx basically give us. So now we have a function of two variables. Because I used two variable because I can illustrate it, so I can graph it. Okay, so that's why I choose this function two variable right here to demonstrate. For function two variables, and what exactly is d partial f over partial x then? Now I will still start with the definition. Okay, So here's the definition of function two variable partial derivative with respect to x. Okay. So let's take a further look at this definition, right? First of all, let me draw out the surface here, z equal to f of x, y. We all know that when you have a function of two variables, it basically represents is a surface, f of x, y at here. Okay. And second of all, if I go back to this partial derivative definition, as I mentioned, in this case here, what happens is you are changing the x from the current location slightly increased by delta x. At the same time, you are not changing the quantity y, the variable y at here. So basically means if I pick a point anywhere, anywhere in the xy plane. So xy plane, pick a point. So let's call this is x naught, y naught. That's a general point in the xy plane. And now I'm going to do this change according to the definition. So according to the definition, I'm not changing y, I'm only changing the x by small quantity delta x. So basically means I will move, this is x-axis, I'll move to the positive x-axis, slightly, by x plus x naught plus delta x. And y we are not doing any change, so that basically end up over here. So that's the operation, moving that point, the current point, slightly to the positive x-axis direction by a delta x quantity. So that's the operation basically from here to from here to here, right? That's this operation. Is that good? Yeah. And then let's look at the consequence of this change now. So at the original point, if I move up, so this is basically your f of x naught, y naught, right? Or f of x, y. That's this point. That's the point on that surface, when you substitute x naught, y naught into the function. At the same time, if you after the moving, so it's right here, and this point here is f of x naught plus delta x, and then y naught. Is that good? Okay. So now, if I keep moving, consider, let's say if this is actually the kind of a motion we're doing constantly. If you're starting here and you're basically continuing moving along this line, which is parallel to the x-axis, right? Because y is not changing. The only change quantity is x quantity. So if you keep doing this, going from here to the next, and guess what? You should be able to plot out, if you connect all the dots, if you connect all the dots, there should be a curve, traced out on that surface. Is everything good? Okay so far, right? So alternatively, I could also explain this. If I keep going this, and this is a straight line, my drawing, this should be parallel. This is a straight line here, right? It's a straight line. And you can consider it's as if you have a plane. So basically if you extend that straight line all the way up and down, you basically get a vertical plane, right? And that vertical plane will intersect this surface, and then it gives you this intersection, which is the intersected curve, the green one here. It's the same idea. Is that good? Yeah. So that's basically what happens at here. If you're moving along this line, okay, you'll get a green curve at here. And that green curve, of course, passing through this f of x naught y naught, f of x naught plus delta x plus y naught. Okay, so now the point here basically is, as we're doing this change from here to here, then what would be the rate of a change, right? What would be the rate of a change for this function f, okay, going from here to here? Or, in this case, it's decreasing. But if I draw it differently, maybe the surface is going up, it's increasing, right? So the idea essentially is now, what would be the rate of a change, okay, of f x y here, this function, with respect to x change? Okay, so same question, right? Same question at here. And how do you define this rate of change? I guess the easy way to do this is you use the new value, okay, which is this height, minus the old value, and then divide it by delta x, then you get the rate of a change. Okay? Yeah. Okay, so, but I really wanted to, if I really wanted to relate to the function single variable, then I'm going to do this at here, okay? So do it slightly a different way here. Is I will pretend I'm actually have a big eye over here, okay, on the other side of this plane. Okay, I'm going to look at directly, okay, into this plane here. So this green plane, remember this green plane I just draw here actually consists of this curve and this line we're going in the direction of x-axis, right? Yeah. So I'm going to look into that direction. If I look into that direction here, and guess what are we going to see? We see essentially this line here. I'll consider this is some kind of a positive displacement direction. This is the same direction of your x-axis. Okay, and then this is your z-axis, right? So this vertical one here is a z-axis. Okay, and we see what? We also see this curve. So we see this curve over here. Okay. So let me use the green one here. Okay. We see that curve. Okay. And we see the f of x naught, y naught, and also this is f of x naught plus delta x, and then delta y naught. Okay. That's what we see, right? If you put yourself in that perspective and you look into this whole thing. So now talking about the rate of a change of this function, basically you're talking about is, so what will be the change from here to here and divided by delta x. Now if I consider, now if you look at this one here, this is really just a curve, or it's the same kind of curve as we usually describe a function of single variables, isn't it, right? Yeah. So now if I go back to the idea of function single variables, this, as we all know, this is basically the slope, isn't it, right? And when you have a function single variable, this is a slope, or you could consider is you draw a line, okay, tangent to that curve, and then you look for the slope of that curve. That's what function single variables essentially give you, df over dx. So in this case here, I mean, after I do this operation, all I see is as if it's a single variable now. And if I'm looking for the rate of change of the function, essentially equivalent to looking for the rate of change of this curve at here. In other words, the rate of change is represented by the slope of this red line here. Okay? Yeah. That's the idea of partial derivative, basically. Yeah. So you can see here, so the slope, so basically the slope of this curve, okay, at x naught, y naught location. Remember, this is the slope of the curve at this location here. I draw it here, I can also draw it here, so I'm going to draw that straight line over here. Okay, so this is the same tangent lines. Okay, these two basically the same thing. Okay, right. I just put it in a flat plane now for this one here. Okay, so this slope of the curve at here, okay, is basically the partial derivative of this partial f of partial x at x naught, y naught location. Yeah. So now you can consider, instead of just a pure partial derivative at a certain point, you can try to visualize, especially for function 2 variables. Okay, you can visualize, okay, so the gotta represent the slope of a certain curve, and for a particular point, x naught, y naught, then it's the slope at that point of the curve. Okay, yeah. And very shortly after the midterm, okay, we're gonna have basically a different idea of slope. Okay, so you see, the one we're moving at here is in the direction, what in what direction? It's in the positive x-axis direction, right? Okay, so basically we're saying if you're walking in the positive x-axis direction, and I'm interested in the rate of change of the function f, then I will do the partial derivative. Okay, now what if, right, you have actually completely different direction? So what if you're actually walking, okay, that's not the good direction. What if you're walking in an arbitrary direction? So in other words, we have x naught, okay, plus delta x, and then y naught plus delta x. Okay, that's a possibility, right? Yeah. So you can walk in the complete direction to have a slight change at it here. Now this is not for today's topic, but for the next week or week after. So this is basically give us the so-called directional derivative concept. Okay, yeah, directional derivative. So as you can see, partial derivative is a special kind of directional derivative, because partial derivative basically means it's a derivative representing the change in this case here in the x-axis direction. Okay, yeah. So keep in mind, and we're going to cover this later. Okay, but for now, okay, this one is quite simple. It just represents the slope of a curve, okay, at a certain point. So let's look at another example, okay, in terms of partial derivative, to get more comfortable with the computation. Any questions so far? Yes.
For that black, the red here was just like y 0 plus delta x.
Actually, I should sorry, I should draw this. I think I should draw this over here. So this is your starting point, and then moving to this point.
So y 0 plus delta x.
Oh, that's so sorry. You're absolutely right. Delta y. Yes, excellent. Yeah, good. So this is very exaggerated. You know, delta x, delta y, not necessarily this much at here, but it just means you can do an arbitrary direction change, okay? Which you're also interested. If I go this way, then how's that surface, right? How's the surface elevation change or rate of change? Okay, that's basically the idea of directional derivative. Very useful concept. All right, let's look at one more example at here. Okay, this one here is relatively a little more complicated. Okay, this is actually one of the midterm questions maybe 5 or 6 years ago. Okay. Here is a function 2 variables, and we want you to, let me see. Okay, so verify. Verify that this expression equal to 0. Okay. This is actually a fairly common partial differential equation. Okay. So as we explained, okay, the order of this partial differential equation is second order. Okay. And you're learning, right now in 246, you're learning ordinary differential equation. So solving a differential equation which essentially consists only function of single variables. You're learning how to solve that To solve that, you get an analytical solution essentially, right? Now, very similar, you can have a second order or even higher order partial differential equation. There are actually different ways to solve partial differential equation, but in this case here, it's more or less like give you the answer. So suppose this is the answer of the partial differential equation, and wants you to verify if this is the answer of the partial differential equation or solution. A proper name of this partial differential equation is called Laplace equation. This is a Laplace equation in 2D. If your function 3D function of 3 variables, then you can easily extend that to another one here. Basically, you add one more term if you have a function of 3 variables. It's a very common function in heat transfer partial differential equation. So in our case, I'm not going to try to show you how to solve this analytically. We're just trying to verify this answer. Alright, verifying basically means you look at this one here. I'm going to try to calculate what is this second order partial derivative and what is this one here after substituting the solution into this expression. Both of them are second order, so basically means you have to calculate what partial f over partial x is, and then what partial f over partial y is. Right, that's the way of thinking. Once you get these two partial derivative, first order ones, then you can further calculate based on the result to get this second order. Right, so this is basically your second order partial derivative to get another partial derivative based on the results, and similarly for this one. So that's how you would approach this computation in here. So I'll just calculate this one here, and then you can you can exercise the other side. Alright, so let's start from here. So what is partial f over partial x? So let's write down partial f over partial x. Now, the operation wise is, so when you're taking partial derivative of the function with respect to x, you can literally just put a big bracket here and then write down the whole expression of the function f and then put it into that bracket. That's what you're doing. You're calculating the partial derivative of the whole thing with respect to the x. Now this is also something I wanted to emphasize too. Since we're learning math, I really wanted to explore all of you guys to follow the proper way of writing a mathematical expression. I know a lot of time you know what you're doing, but your writing doesn't actually reflect what you're doing. So a lot of time a student writing this portion out of here, I have seen many different ways of writing this kind of thing. Basically, instead of writing this, they probably just partial bracket 10, like this, and then they keep going for the rest of the things here, right? Technically, this is not right, even though you know what you're doing, and also it's potentially risky that you are actually gonna trick yourself even into something completely different operations, right? So I would like that you stick to all the standard way of writing things, at least like this. So now coming back to here now, remember this is function of 2 variables with respect to x out of here. Literally you could use that the chain rules that we have just covered. So let's say I'm gonna let u equal to y over x first. U equal to y over x. So now this function in here, then this function in here, basically I could see, then you can see this function f equal to tan inverse y over x becomes tan inverse u now, right? Okay. So then partial f over partial x, okay, can be written as straight f over du. So you take the derivative f over u first. Now remember here I didn't write, look at here, I didn't write a partial sign. Because why? Because if I do this substitution, then f is just single variable u now, right? Function u. So I don't need a partial f here. But however, next step, okay, u is multivariable function, then we can use partial u over partial x. Is that good? Yeah. So that's sort of like a chain, not a chain rule, a chain rule here. Yeah, it is a small, simple chain rule here. Okay. So now the question here is, let's look at this. Then what is df over du then, right? What's df over du? This is tan inverse u. Now this is something if happening in the exam, which I will give you basically a formula for that. So when you take inverse tan function, okay, so this is inverse tan function over u here, the result is 1 over 1 plus u squared. Okay, yeah. I think a lot of you probably still remember this, but I don't require you actually remember all of this all the time. Okay. Okay, so now I'm gonna plugging everything now into this formula. So basically, what we're looking at is first calculate df over du, and then calculate partial u over partial x. So I have 1 over 1 plus u squared at here for this term, and then I have partial u over partial x. So this is just y over x basically. So we treat which variable as a constant? Y. Okay. So when you treat y as a constant, if your mind doesn't believe you, then you can temporarily replace the y with a real constant. Okay. But then you have to put it replace it back. And this gives you negative x squared y. Okay, so for this derivative, right? Yeah. So I think everybody knows what derivative 1 over x is, of course. Right? It's negative 1 over x squared. Okay, so I'll put the u back. U is y over x. Okay, so that's the first order partial derivative. Now you don't stop here though, huh? You should try to simplify this kind of results as much as possible into a simple fraction. And a lot of time things can be simplified. The denominator here is y squared over x squared. And then here is basically x squared over x squared plus y squared, negative y over x squared. So overall, negative y over x squared plus y squared. Okay. Incidentally, I know this is actually high school, probably grade 8 or grade 7 kind of stuff. Yeah, because I'm helping my kids doing this. Hell of trouble doing these simplifications. So, and I would expect some kind of trouble within you guys too, because I've seen that. So try to practice this kind of fraction. Because if you don't simplify, because a lot of people don't simplify and then carry over to the next computation, and I can guarantee that not gonna be pretty when you just directly doing partial derivative over these results. Okay, so now we carry to the next level. Okay, calculating the partial derivative, the second order partial derivative. Okay. So what basically this means, we calculate another partial derivative with respect to the x using the results from the previous step. Okay, so now this one here, I don't think I'm going to use any chain rules because this is relatively simpler expression here. So all I need to remind myself is I'm going to, because I'm taking partial derivative of x, I'm going to treat the y as if it's a constant. Okay, so in this case here, because there are two terms, fraction, then I will use that quotient rule, okay, for single variables. Because really we're just calculating like a derivative of single variable because I'm treating the y as a constant. So this is where you have to be extra careful at here because your y doesn't look like constant at all, right? And then it's not a constant, but you have to treat it as a constant. So let's take a look at the application of the quotient rule. Alright, so I got a negative at here, and I'll leave the negative outside. Okay, leave the negative outside here just for the simplification. Then v squared is x squared plus y squared squared. U prime, so u is the y at here. Okay, u is the y. So u prime basically means what? In this case, it's actually it's partial y over partial x. Right? That's what u prime here means. So in other words, the first term is this u prime must be 0, right? Because you're treating y as if it's constant. Then we all know the derivative of a constant is 0. So the partial constant in respect to y, of course, is 0 too. Okay. Then minus the second term, v prime u. And v prime, v is bottom here. So it's the derivative, the bottom, with respect to x. That's what v prime is. And you treat a y as constant. So the derivative of the bottom with respect to x gives you 2x here. So because this is constant, then the derivative of that constant with respect to x is gone. Times u, and u is y at here. Okay, so you put it back here. Okay. So that's the results. And then negative and negative cancel each other. So you get 2xy over x squared plus y squared squared. Okay, so that's it. That's the results of the partial derivative, right? Here is your second order one here, of course. Okay. Then you can use a very similar approach to calculate what partial f, second order partial f over partial y, and of course you will get the results negative at here. Then you add each other together, you get a 0. Okay, and that's how the Laplace equation, okay, here is verified. So basically, this guy here is a solution, right? Okay. As a matter of fact, we call it the particular solution, just like ordinary differential equation, it's a particular solution. Partial differential equation often have many particular solutions. This would not be the only one. Okay. There can be any other, maybe it can be other type of particular solutions. Okay. So the emphasis is basically just always, okay, always be alert. Okay, which is being treated as constant. Okay, so there's something you have to be always alert. Which variable am I taking the partial derivative with respect to? Then which other variables I'm going to take it as a constant? Okay, because your mind will always play trick with you. That's a fact. Okay, so I used a couple of properties at here for the calculation of a partial derivative. So maybe I'm going to summarize a little bit in terms of these properties or rules. Okay, so mainly there are chain rules here. We're talking about it here. Okay. Even though I don't write this chain rule down, this one here, I think by a natural instinction, you actually will apply this rule set here very easily. Okay, so the first case of the chain rule here is this: given, let's say, function of two variables, okay, and the x is a function of t, and the y is also a function of t. This is very much like the scalar line integral we have done. So you have a parametric equation. You have a function of two variables defined, then you integrate over the parametric equation. In that case, your x, y's are function of t, right? So then, if we're going to calculate this df over dt, so the chain rule right here is you calculate partial f over partial x first, then dx over dt. Partial f, partial y, and dy over dt. Okay. Which can be simplified to in a different symbol right here. Okay, so, and that actually not necessary. Okay, I'm putting the bracket because I will write this down in the future lectures. So for the results at here, I can also write it in the dot product format. Okay. Right, you can see that I can define a vector as fx, fy here, and I can define another vector dx over dt, dy over dt. Then for this particular derivative, it becomes just a dot product between these two vectors here. Right? Okay. Incidentally, this is what we're going to cover next. This is basically called the gradient. Okay? This one here. So, but not for today's topic. That's the first kind of a chain rule at here. Let's look at the second case. This is one a little more common. If we have function two variables, for example, x can be another function of two variables. Similarly, y can be another function of two variables. So if you plug in the x, y into the function f, then you end up with basically function f is ultimately a function of u and v. And if we are going to calculate, let's for example, what's the partial derivative f over u, then the chain rule in this case is take the partial f over partial x first, and then partial x over partial u next. Partial f, partial y, and partial y over partial u. That's the chain rule when you have a function in chains like that. Okay. Similarly, you can write down partial f over partial v. So I'll just write down here. Okay. Alright, that's the chain rule for these two cases. I think in most of the time these two cases covers pretty much the type of chain rules we'll use in this class, okay, for partial derivatives. Now, I do want to point out one thing at here, okay? This is I feel like sometimes if I don't point it out, actually you probably won't make a mistake, but if one point it out, and you might make a mistake, but I still wanted to point it out. So, consider this function single variable. and your y is a function of x, and x is a function of t, then we all know that if I do if I do the derivative f over dt, and the chain rule is basically df over dx first, and then dx over dt, right? That's the chain rule. Okay. Yeah. Now, when you do this step right here, right? I mean, literally, you don't really need to do this, because you could also, you could substitute this x equal x of t into the function first, then you end up with just function of a t now, right? And then you take the derivative f over t. And that's equivalent, but basically to say df over dt. Or in other words, if you look at the expression here, the equality maintains once you cancel this dx out, which is df over dt. Okay, that makes perfect sense. It makes perfect sense. However, if you know this is very well, and now you look at this one here, right? You look at this one here, and you may wonder, oh look, I got a partial x here, partial y here. Can we cancel this like we cancel this? Right? Now that is a pitfall here. So that's actually the difference between partial x and dx. Okay, so dx, if you recall, that is called a differential. Okay, it's a differential quantity. What's a differential quantity? It's an infinitesimal small quantity. However, it is still a quantity. Okay, it doesn't matter how small it is. It physically can be described. Okay, it's tiny there. It's there. So I can use a quantity to describe something, right? That's called a differential. But this guy here, it's not a quantity. As a matter of fact, it really doesn't exist at all. Okay, it's just a mathematical symbol, partial x. So that's not a quantity. If not a quantity, then you can't cancel, basically. Okay, so that's the idea. So these two, okay, they are not the same. Okay, you got to be careful with this. In other words, you cannot, like this in this chain rule here, don't try to cancel these terms, right? Because that would end up with a completely wrong answer. So that's the difference between these two. Okay, so I do have an example, but I want to finish the last concept first, and then if I got time, I can come back to do an example here, because the other concept will be included in the final exam, so I need to cover this today. Okay. It's called a total differential concept. Any questions so far? So good in terms of partial derivative? Okay. Yeah, you just have to be confident. If you're confident with your derivative single variable, then you have no problem at all with function of multivariables derivative. Okay. Yeah. Total differential. So how do I approach this? So let's still start from very simple case at here. Consider function single variables. Okay. Yeah. Now, for function single variables, and if I plot it out, okay, this is a very simple curve in 2D, of course. Okay. If I start from a location of x and go to a location of x plus delta x, so there's a small increment of delta x and here. Then, and of course, x corresponding to f of x, x plus delta x corresponding to this one and here. Okay. You can basically find the actual function change. Okay, if you compare the differences vertically. Okay, so that will be the actual function change, right? Okay. Now, what if I so delta f, okay, equal to f of plus delta x minus f of x. Okay, that's your change in here. So what if I wanted to just to approximate this delta f at here, right? Yeah. Then in the first year you learned, okay, so one way to approximate is, okay, let's draw a tangent line at here, okay, which is essentially you draw a line with a slope of df over dx, right? That's a slope. Okay, draw a tangent line. Now, if I don't want to have the accurate function change, then I could use a approximation here. So use this portion as the approximated function change, right? Delta f. So this can be used as approximate. So this portion, right? This portion is, you can calculate using the trigonometry here, because this is a right triangle, and this is the tangential theta, which represents is the slope. Okay, so theta here is the slope. Okay, then you can easily calculate this vertical length, okay, by using the delta x at here. Okay, so that basically gives you tangential theta, which is df over dx times delta x. Okay. So that gives me an approximated change for delta f. Okay, approximate change for the delta f at here. It's all good? Okay. Now, it is approximate change because you have a delta x at here. However, okay, now if delta x actually goes to 0, so you let the delta x shrink as small as possible, then the delta x becomes dx. So the delta will become the differential quantity, straight d now, right? Straight d. Then in this case, your df over dx times delta x becomes just times a dx at here now. Okay, so this one, okay, instead of approximated change, then it's not approximate change anymore because it's so small. Then that change at here will become the same change as this actual function change. So we actually use small df, okay, to represent this accurate description, which is also accurate because you know exactly, because you can cancel these two, right? You can cancel these two here. But I would rather write df over dx. I would rather write just maybe just like this. Okay, so df equal to the derivative f prime times dx. So very much like the results like this. If I have a y equal to x squared, then this is f of x. I know f prime x is 2x. Then I would write the df equal to 2x times dx. Okay, this is the idea. Now this is actually basically called a differential, right? As I keep saying this. Okay, this is called a differential, and this is function single variables. Is all good? Yeah. Yes. Where? On the right side. Here? At the bottom. Oh, it's a dy. Oh, yeah. I mean, I can write df. Yeah, because because I have y at here, so it shouldn't make should be the same. Yeah. Yeah. Okay. Very good. So I want to emphasize this differential concept here. Okay. Emphasize the differential concept, and also we're approximating basically this curve using this straight line here. So if I call this straight line, call it a line of L at here, then that line equation Okay, you can derive the line equation easily, which is basically any equations. Let's say if this is x at a location, right? Then that's your line equation, right? That's your line equation. Okay. And this is your basically line approximation. Okay, line approximation of curve f of x, y at x equal to a. Okay, yeah. So all of this essentially it's not new. Now, line approximation of the curve equation, as to further review here, it could be, if you recall that this essentially what the first two terms of the Taylor series expansion for function of f of x, right? Yeah. So if you take only the first two terms, neglecting all the higher terms of the Taylor series expansion, you get this line equation, the approximation of the function f of x at here. Okay? Yeah. So I'm doing all of this is trying to set up the stage for this function two variables here, the total differential. Okay? Now let's consider a function of two variable now, because I can graph function two variables. Okay. And I'm going to draw something in here. Okay, so here's a function f of x, y at here. Is that good? Okay, here's a function f of x, y. Okay, now I'll do a similar analogy. So here we're increasing x equal to a to an adjacent location by a small increment of a delta x. So I'm going to pick a point at here, call it x naught, y naught, for example. Okay. And then I will go to the next location. Okay. And the next location is x naught plus delta x, y naught plus delta y. It's a small position change from current x naught y naught to adjacent x naught plus delta naught and y naught plus delta y. Now what that means to the given function basically means is you have a two corresponding function f value, and of course here is f of x naught y naught, and here is and f of x naught plus delta x, y naught plus delta y. Okay, yeah. So here is the idea now. Okay. Now, if you look at this function single variables, I try to get the small change in the function f due to the change of this delta x at here, which I use delta f, right, to get the change. And this change is obtained through an approximation, which is this straight line at here. Okay, so you obtain approximated change by drawing a tangent line at here to approximate that delta f change. That's how we approached the function single variable. Okay, yeah. So then how about this surface then, right? Then you have from here to here. Can I use a similar analogy? If it's a curve in the xy plane, I can use a straight line to approximate the change of the function f. Then in 3D for a surface, instead of using a straight line to approximate the change of this function f, what can I use to approximate? So from here to here, instead of thinking you're moving along an actual surface f of x, y, an alternative is what? Instead of a line like in the scalar function, one single variable scalar function, I could also use analogy here. Instead of a curve, instead of a straight line, I can consider myself a what? A tangential plane, right? A tangential plane at here. So if I can draw a tangential plane going over that x naught, f of x naught, y naught, this location here, I can use that tangential plane to approximate the change of the function f, the actual function f, the surface. So this one here is a tangential plane, okay, to the surface at x naught, y naught, and then fx naught, y naught location. Okay, so x, y, z, right? This is 3D coordinates. I can consider to use a tangential plane to approximate that surface around this location. Then instead of an actual change delta f, I can use a change along the plane as the proximated change. So how do I get the tangential plane then, right? And here's how you can get the tangential plane. We can use this, basically the Taylor series expansion for the f function of xy at x naught, y naught location. Okay? Yeah. So what's the Taylor series expansion for multivariable function? And I'm going to write it down in here, okay? It's f of xy and equal to f of xy x naught, y naught, and plus fx x naught, y naught, x minus x naught, plus fy x naught, y naught, and times y minus y naught, and plus all of the higher order terms. Okay, that's Taylor series expansion for a function of two variables. So this symbol here basically means higher order term. Okay, this is higher order term. Okay. So what do we mean by approximation? Basically, we neglect all the higher order terms. Then we only keep the first three terms at here. Okay, only keep this portion. So these three terms can be used as an approximation for the f at here. So what we do is we can simply basically say my function fxy is approximately equal to the three terms. Okay, so that's the idea. We use the three terms, these three terms at here, as an approximation to the original surface f of xy. By doing this, so if I only look at the right side here, okay, let's take a look at the right side. What does the right side actually give us? So let me define. I'm gonna just single out the left side here. I'll let a symbol L equal to, or you can call it W maybe. W of xy equal to the whole right side. Okay, and let's take a look at what does this whole thing here actually represent. Okay, that's your right side, three terms, right? Three terms here. Okay. Now this is a little bit different from what we usually write z equal to something, right? But here I'm writing w equal to this because I don't want to confuse this with the original z here. Okay? But this side here basically is like a z variable. Okay? It's a vertical variable z. Okay? Now, if you look at this one here, it should actually remind you something. Remember remember the formula for plane equation is what? The formula for plane equation is A times right. That's the formula for plane equation, isn't it? Right? Yeah. So if I compare the results, basically this is your first few orders, first three terms of the Taylor series expansion. If I compare this expression with the plane equation, let's look at this. Not quite exactly the same because here you have a z here. Maybe I'm going to move this one over to this side at here. Okay, but irrespective, if you look at this, this is x minus x naught. This is y minus y naught, right? And this is your partial f x at this location, partial f at this location. That's your a, that's your b. That makes sense, right? Yeah. And the trick part is this portion, isn't it? Right? It's this portion. But consider if I move this z, okay, over to this side at here. What do I get? Basically, I get negative z plus f of x naught. Y naught, right? If I move this to this side here, okay, and if I take the negatives out of here, and I get basically z minus and this, okay, and then the whole thing equal to 0, okay, this plus this. So that's exactly the same format now, right, as a plane equation. The c value here equal to -1, right? -1 here. So basically, what I'm trying to say is, see here, this whole right side here is used to approximate the function f, and what we used here is basically a plane. Okay, it's a plane here. Now you may ask is, because I do mention it's a tangential plane, right? It's a tangential plane. Okay, so why is it a tangential plane? So tangential plane basically means it's a plane at this location tangent to the surface at that location. That's what it means. So what makes it a tangential plane then? Then that plane got to have a normal vector, okay? Normal vector perpendicular to the given surface. So this is actually for the future lecture now. So here is the normal vector A, B, C. Basically you have a normal vector here, A, B, and then C. Okay, normal vector. And in the future lecture, we're going to be able to prove that this ABC is perpendicular to the surface at that location. So this literally just gives us this plane here. It's a tangential plane to the point. Okay, to which point? To this point. Okay, at that location. Is that good? So leave that a question mark for the future. Why is it tangential? We'll prove that in the future. But for now, let's coming back to this one here, right? To this expression again. So I'm using this plane to approximate this function f. Then here's what I'm going to do now. I'm going to move this f of x naught y naught to the other side here. Okay, to the other side. Is that good? Right. If I do that, so basically I move this one to the other side, okay? I'm gonna basically do this. So here's my change then, right? I'm gonna let x equal to x naught plus delta x, and y equal to y naught plus delta y. Okay. So if you look at this, is the whole idea, because I'm moving from x naught y naught to x naught plus delta x, y naught plus delta y. So that's why we're letting x, this new x, to be x naught plus delta x, new y to be y naught plus delta y. Then coming back here, so this f x y becomes f of x plus x naught plus delta x, y naught plus delta y naught. Then minus that f of x naught, y naught. Okay, yeah, minus this here. So basically we're moving this term to the left side, okay, to the left side. And then it's approximately equal to these two terms, okay, these two terms. So approximately equal to f of x, x naught, y naught, and then x minus x naught, and fy, x naught, y naught, y minus y naught. Okay, plugging the x, y here. Okay, plugging this y over here. Plug the x over here. Okay. Then what does this side give us? Give us now. Give us fx at here, delta x, and fy at here, delta y. Okay. Once you plug in here, and this side here. Okay. This is your initial position f function value. This is your final position f function value, and in total it's approximately, right? It's basically the actual change, the delta f. So now you have delta f equal to this multiplied by delta x and this multiplied by delta y. Okay, yeah. So it's approximate sign because it's a relatively bigger quantity delta x. But if I move this to 0 and move this to 0 at here, now I have delta f. Okay, instead of delta f now, all of the delta will become a straight differential, become differential form. Then the df, okay, instead of approximate now, because now it's small, so small, it becomes basically exact term now. Okay, yeah. So this is the results here, what we call the total differential, basically. Right? You can see here is a idea, the so-called total differential. Okay, and you have two partial derivatives at the location x0, y0 location, and then you have this differential dx and dy at here. The only difference is we added a keyword called total compared to the single variable. Okay, yeah. An alternative writing, this is writing at a certain specific location. You could just, if it's a general location, then we could just write as simple as this. Okay, so df equal to fx dx plus fx dy. So this is partial f over partial y. Okay. Okay, that's total differential. Let me go over a very quick example at here to what total differential is. Okay. So I'll use that example that we have just gone through here to illustrate. That's the function, multivariable function, the inverse tan function. Okay. Now if I ask you to do this, can you write down the total differential for this function f? Okay, for this function f. Then what you do is you follow this formula exactly at here. Then df basically equal to partial f over partial x dx dy. Okay. I would like all of you to write this formula for 10 times, which won't take you more than 1 minute. Okay. This is the formula. So don't invent a wheel. You cannot have any other different format from this total differential definition. Okay? Yeah. If I ask you what's the total differential given certain function, this is first thing that you need to write it down. So partial f of partial x, partial f partial y, we have calculated from the previous example, which is basically these two terms. That's it. If that's the question asking you what's the total differential of that function, you stop right here, that's it. Okay? All I'm saying is, because I've seen a lot of people without writing this dx dy at here. Okay, it's part of the formula, right? It's part of the formula. You cannot just let it go because without having these two terms in here. Is that good? Yeah. So I'm running a little bit of time, but there is a similar assignments, okay, in assignment 3. Basically, considering actual numbers like this, right? Actual numbers, and what will be this small change at there? So take a look at that. I'll go over this example next in the Tuesday lecture next week. Okay? Yeah. Any questions? All good?